Okay, go ahead.
Has that come through as full screen?
Yes.
Okay, good. So welcome everybody. I'm giving a short presentation on how Python is used in HPC, which is used for simulations at scale. The whole point of scale is to work with very large simulations. And so, as the subtitle says, this is all about high performance computing, which is what the center of high performance computing is for science. So let's just quickly start with a brief definition of what high performance computing is. So it's a collection of algorithms and techniques that utilize parallel hardware to accelerate scientific computation and solve very large research problems. I've highlighted the important phrases and terms there, which is the parallel hardware. So you need to have a parallel computer in order to implement high performance computing. And your goal is to solve a very large research problem by accelerating the computation of that problem. So the key thing to keep in mind is that high performance computing is large computing, not really fast computing. The idea is to do big science first. Now, an important subset of high performance computing is high throughput computing. And that's characterized by many independent tasks where there's no communication between the tasks. And you can probably see where we're going here, that if you have a lot of independent tasks, then you already have a lot of capability for doing parallel computation. And in high throughput computing, those independent tasks are typically operating on subsets of your data. So you might have a very large set of data, a very big problem you want to solve, but you can actually divide it up into subsets where each set can be processed independently of the others. And so there's actually no sharing of data between those individual computations. The reason I mention this is that a lot of what we see as a large scientific problems at the HPC that come from outside the traditional simulation subjects like physics, astronomy, climate, engineering, and so on, actually is high throughput computing. And that, by the way, includes machine learning, which of course is a big topic on its own. So what we have at the CHPC is a cluster supercomputer. And so the way that that's put together as a parallel machine is that it's many individual compute nodes that work together, they communicate and share data over a network, and their intention is to calculate the numerical solution to a scientific problem that is too big for a single computer. So you can see that a cluster supercomputer is designed for high performance computing. And that leads me to distinguish between the different types of parallel hardware that you will find both in a supercomputer like the CHPC's cluster and also in your own computing hardware, whether it be your laptop or even your cell phone. At the coarse grain, this is the macroscopic level, we have the supercomputers like the CHPC cluster. And these are usually distinguished by shared memory. That's a lot of cores in a single computer or compute node. And this is typically what your laptop or desktop workstation is, right? And then distributed memory is taking multiple instances of those computers and networking them together into a cluster. So that's the top level approach to parallel hardware. And this is usually where the major design is needed to create a parallel program that can work at this level. Then there's also a fine grain parallelism. That is the actual compute chips. And this goes down to cell phones and other similar small devices, is that because they actually have within them the ability to compute their own internal instructions in parallel. So these are superscalar pipelines, vector processing units. As their name suggests, they're actually optimized and designed to work on doing vector arithmetic, including matrix arithmetic quite efficiently. And then GPUs. GPUs are just cases of a chip that's designed around having many individual arithmetic logic units that can be harnessed together to do either vector processing or similar processing, but over very large arrays of data. GPUs, of course, also have some additional features because they originate from graphics. But we're not really worried about that since we're not covering visualization. And there are two main types of parallel problems. So when you have your big scientific problem, you come up with a numerical method to solve that problem. You want to look at it and see what is the parallel capability for the tasks. In other words, how many tasks are independent of each other that can be executed in parallel. And also data parallelism. And this is really the heart of why we're talking about HPC being for big data, for large scientific problems. Because the more data you have, typically, the more potential you have for parallelism. And looking at these two, and most HPC simulations are actually a combination of both. But these will determine how the computational work is divided amongst the actual computational units. And that's the heart of parallel programming, is the program organizes the work amongst the hardware, which can be, when I say computational unit, I could mean a whole compute node on a cluster, or it can be all the way down to the fine grain where it's an individual arithmetic logic unit within a GPU. The important thing to keep in mind here is that data parallelism. In other words, if you have a very large problem, the larger problem with the more degrees of freedom, you can actually find more task parallelism. For those interested, if you want to read further on this, look out for things like Amdahl's law and Gustafson's law, which model these and describe how the ratio between serial and parallel capability determines how much you can do in parallel, and how the larger your problem size is, the more parallel potential there is. So let's look, starting out with a typical numerical problem, which many of the applications you use would actually be using at their heart. That is to solve a very large system of linear equations. And because it's a sparse system, you typically wouldn't use a direct method. You use an iterative method like, say, a conjugate gradient method. And the good thing about conjugate gradient methods and related methods is that not only can they solve a system of equations, but they can also solve a minimization problem. And that's used, for example, in machine learning. But the key thing about these equations, the method described, presented here, is that if you look at the entities, all the characters that are in boldface represent vectors and matrices. And that's where having a very large system means you have very large vectors and matrices, but those vector matrix operations have a lot of both task and data parallelism in them. So those all have potential to be done in parallel. However, if we look at it from a macroscopic point of view, you'll see there is a serial nature to it. So if you just look at the first line of the algorithm here, the vector R is calculated and then the vector D. But the vector D cannot be calculated until vector R is fully calculated. So that dependency means that those three statements in the first line have to be done in that order. But individually, those statements, because they represent vector matrix operations, they can be done in parallel. There's also a loop, and loops on another place where we look potentially to see how much work can be done independently or not. Anyway, that is probably a complicated algorithm. Don't worry about the details about it. Just as I say, the key features is that there is a lot of intrinsic parallel computation in here. So let's drill down into just one of those examples at the fine level, fine grain of computation, vector addition. So let's say we have 3 vectors and we want to add up the elements of 2 vectors, find the vector sum and put it into the third. So this is just using pseudocode, which is based on C or Fortran, which is very similar. We just say we have these 3 arrays, each of length n because they represent vectors. And vector addition only makes sense if they're all the same size. Double just indicates that they are double precision numbers. I, which is going to be the loop at the index through the vectors, is obviously an integer. And then you can see pretty straightforwardly, you are adding up each element independently of the others. So that's where you're looking at, because they're all independent operations, actually doing that in parallel. Now, this is usually referred to as a SIMD type situation, where you have a single instruction, here addition, but it operates on multiple data. Here are all the elements of the 2 arrays. And the diagram there just says you have the instruction pool, single instruction addition, goes to the individual processing units, and they pulling in, here in this diagram, you have 4 processing units, they're pulling in the elements from 1/4 of the data at a time. Now, if we go to the next level up, let's say we actually have a very simple system that has 3 CPU cores. Those cores have access to the same memory, obviously, so this is a shared memory system. Then if you have 3 processors, 3 cores that you can do the vector addition over, then what you do is, as illustrated in this pseudocode, you take those 3 elements, those 3 arrays, and you divide the elements up across them. So now your index I is going to loop from 1/3, 2/3, and 3/3. And each third of those arrays will be added independently, 1 to each process, numbered here from 0, 1. Oh, that should be P2. Sorry, that's a typo. And that can actually be done in code. You can actually instruct your compiler in C or Fortran to actually do this using what's known as OpenMP. And the way it's done is you add this extra pragma, which is just an instruction to the compiler, that for loop must be executed in parallel over however many cores there are. And the nice thing about OpenMP is that you don't have to worry about how many cores are. When this code is actually run by your system, the operating system will actually tell the code how much cores there are, and the division then is done for you. Now, obviously, you're learning Python programming, and you're learning programming for the first time for many of you. You don't need to worry about this, because you'll be using Python, which will be doing this for you behind the scenes when you pull in the appropriate libraries or modules, which I'll mention later. So that's fine grain parallelism. Let's go to the next level, the coarse grain, and let's look at a cluster, which is a distributed memory machine. Here you have 3 individual compute units, and these are what we call compute nodes. And each node is essentially a whole computer. On our system, there are multiple cores, there's lots of RAM, so there's like 24 cores, 64 gigs of RAM, or 128 gigs of RAM. But they're all connected to each other with a very high-speed InfiniBand network. So what's actually has to happen here is that you have to have a program running on all three of those compute nodes that will do those computations for you and will share the data between them over the network. Now, you didn't need to worry about the sharing of the data in the shared memory because the cores there all had access to the same memory. Here you can see the memory is actually distributed amongst the individual compute nodes. So yeah, lovely. This is where Python actually excels because you can do this at a high level because this is coarse grain parallelism. You're doing it at a higher level than the fine grain parallelism. You don't need to worry about compiling down to the machine code level, as it were, which is what you would do with Fortran or C. Instead, here you're saying, okay, I'm looking at my overall problem and I'm doing a decomposition of the data. Very often, this is known as domain decomposition. And this applies to many features in simulations. Let's say you're doing a fluid dynamics simulation of some volume. You would divide that volume up into subvolumes and you'd give each subvolume to a compute node. Obviously, because whatever fluid is in those volumes has to can flow between nodes, you have to make sure there's some communication between the compute nodes to accommodate the surfaces that are shared. But let's keep it simple. Let's look at doing the inner product, the dot product, using MPI. So it's pretty straightforward in Python. You'll obviously learn what all these features of Python mean as you go along. And so NumPy is just pulling in the numeric Python library, so you actually get arrays. Then the MPI for Pi module is actually going to provide you with the MPI commands. Then you define a function which does the dot product, but it's called serial dot because it's done in serial fashion. This is not done in parallel. This just does the inner product sum for that portion of those two vectors that this compute node is going to operate on. Remember, this has to operate over multiple compute nodes. So each compute node will be doing its share, a portion of the global, the total X and Y vectors. And that's accomplished with a parallel dot, which is first going to compute the serial. In other words, I do my part of it. And then it's going to say, okay, I have the local sum. Now I'm going to broadcast it by the reduce command to all the other systems so that all of them can be added up together. And that's just how those functions are used. You have set up two vectors. Obviously, they'd be much larger than that. And the vectors would have to be properly distributed across all the nodes. So I am glossing over quite a few details here. But notice where you have the MPI world get rank and MPI world get size. There you're just setting up the fact that because you're using MPI to actually distribute the work, you have to put in the appropriate Python commands to actually set everything up. And you can see there with the next line where you are actually working out which portion of that global vector does this compute node have to calculate. So it calculates it with the serial dot and then calls the parallel dot to share that result amongst all of them. And then the last statement there, the if statement, if my rank equals 0, print dot completed. In other words, only one of the multiple individual processes, the one labeled 0, that's called the rank, and it's just an index into the processes, will actually report the result. The MPI finalize just ends everything. Now, don't worry if you're not understanding this. The important thing is to get the big picture, which is that you have this very large problem, these very large vectors. You need to distribute the work of calculating the inner product of two vectors across multiple compute nodes. And you can do that in Python this way. So going back to Python, Python has fine-grained parallelism. It can take advantage of parallel hardware at the lower level, like, for example, your vector processing units, your multiple cores, and it does that for you without you having to worry about it. So if you're doing a lot of matrix or vector operations, when you include NumPy to do those operations, and a lot of other modules will depend on NumPy as well. You'll see when you do look at the data processing modules is that you defining NumPy arrays a lot for plotting, for reading in your data from a CSV file, and so on. But the actual operations that NumPy is doing is actually done at the low level, taking advantage of whatever parallel hardware your computer has, whether it be multiple cores or it be vector type instructions like AVX, for example. And generally that comes out of what's known as BLAS, which is the basic linear algebra subroutines. So those are very efficient versions of, and they are optimized for the hardware that Python is running on by programmers who've specialized in doing that work for NumPy. So NumPy just uses that. And you don't need to know the detail at all. You just need to say, okay, well, I've got these two arrays and I need to do an inner product with them. I just call from Python the appropriate NumPy function to do the inner product. Similarly, if you're using a GPU, you can use PyCUDA. I just mentioned, very important point is that PyCUDA uses CUDA, which is specific to NVIDIA GPUs. But you can use PyCUDA for similar operations as you would do. In other words, instead of operating on your vectors or arrays on your computer, you're operating on the GPU, you just use PyCUDA to set everything up. And you don't need to worry about those details. You just use PyCUDA according to the PyCUDA documentation, the same way you use NumPy functions, classes, etc., as the NumPy documentation. And that will take advantage of the speed and the parallel nature of that hardware. Now, coarse grain is different. This is where you have to actually start thinking about how do I design the work in my subroutine or my workflow to actually work across multiple CPUs and especially multiple nodes. In other words, how do I divide up the work of my very large scientific problem? You can use MPI, and then you would use the MPI for Pi. Now, that's works quite well for high performance computing, especially where the way that you've divided the work is very uniform. In other words, it's essentially a homogeneous system. You've taken a single volume, for example, and just subdivided into smaller subvolumes, or you've taken your data sets and divided them up into subsets, and essentially you're doing the same operation across all of them. Now, if you don't have that, or if you don't need the inter-process communication of MPI, in other words, you have more of a high throughput computing problem where the data is processed more independently, then you would use just one of the multi-core approaches in Python, so like the multi-processing module. And that has the advantage is that because there's not really inter-process communication, if there's any communication between the compute nodes, it's to perhaps a sort of a managed program, which is scheduling everything. So it can handle variation where your individual compute nodes are different, doing different tasks, and not necessarily need to have the uniformity that you would like with MPI. Now, that operates equally well on a system that is just one computer, like your laptop with 8 cores, or your desktop with 16 cores or 32 cores, or you come across to the CHPC and you want to use a cluster. So both MPI for Pi and then multiprocessing, but multiprocessing needs a little bit of extra, so we say help, and that's, for example, something like Dask, which handles handing off the multiprocessing individual process threads across multiple compute nodes. Whereas MPI for Pi, because it's designed with that, has it already built in. Okay, thank you. I will stop at that stage. Are there any questions?
Thank you, Kevin. Could you just give like a 5-minute overview of the winter school as well?
Oh, sure. I've got the slides from last year. Let me grab that for you. I could do that very quickly. Are they coming through?
Not yet.
Sorry, can you see anything?
No, no slides.
Okay, let me try again. Sorry, did I stop sharing the other one? Maybe that's the reason. Yes, I have stopped sharing. Okay, let me try this again.
Yeah.
Has that come through? Okay.
Yes.
Okay, so the winter school, as its name suggests, is held in winter, which means around July, August to September. It's presented in collaboration with PRACE and EPCC. EPCC is the Edinburgh Parallel Computer Centre, and PRACE is an organisation that pulls together various HPC centres in Europe. The key thing about it is that it's a practical introduction to high-performance computing for scientific and engineering users. So it's 2 weeks of supervised learning. It's entirely online, I should point out, but we have four afternoons a week in those 2 weeks. We will have a practical session of 90 minutes to 2 hours where there's a presentation on the topic, and then there's a chance for Q&A as well as people to start working on a worksheet and then ask questions. In other words, then there's an additional week, sometimes 10 days for the assignments to be completed. All the lecture notes, the videos, the quizzes, etc., are on our Moodle system, so it's entirely online. So it's within those 3 weeks, well, especially within the 2 weeks of supervised learning, it's very much self-paced. As long as you can keep to the 2-week schedule, which shouldn't be too onerous, because as I said, it's only about 2 hours a day of actual interaction. You can work on the rest. And it's preceded by the supercomputing MOOC, which introduces all the concepts you need. So it's an introduction to HPC, a lot better than my very brief introduction now, because it actually goes into some of the details of what HPC is and isn't and how it's put together. It looks at how parallel computers are built, and it looks how they're programmed, and then it looks at how particular computer simulations are then adapted to run on parallel computers. And in the course, what we do is we focus on the CHPC system because it's the major supercomputer in South Africa. What hardware we have, what operating systems and software. We go further on the command line than you will experience here in the Linux environment. We will also talk about, because it's a shared system, the way that you need to actually write job scripts to ensure that the work you want to do on the system can be done non-interactively. So basically, you write a job script with all the work that you need to do, you submit that job script to the system, and then the scheduler decides based on how much hardware you're requesting, when and where it runs. We also look at a lot of how to fix errors. And the real focus of the winter school is how you can turn your scientific workflow into a job script. Because your workflow is typically very interactive. I mean, you'll see in this course that you are doing things interactively in IPython or Jupyter Notebooks, similar. You can easily respond to errors and outputs and change things and so on. But you can't do that when you have a job script. The job script has to run unsupervised without any intervention. It runs non-interactively. And then the other important topic is, because you want to solve big problems and you want to do that in as efficient a way as possible, shorten the time, scaling and performance. And of course, there's also the installing your own software part. And so basically, all you need from that is to learn the basic Linux stuff that you're going to learn here, plus go a bit further, and then work through the supercomputing MOOC, which is free for 7 weeks. And you just work on that before the winter school starts. And that's it. Yep, I'll just stop there. Thanks. So that's the winter school in a nutshell.
Thank you, Kevin. We have run out
My
of time,
pleasure.
so I'm not sure if we're going to have any questions, but they are in the chat channel. So please, can you go on the chat channel and answer them? There's 2 questions about parallelism and Slurm. Yeah, so I can check
Okay.
the chat, respond in the chat channel. Thank you so much.
Are you
and
talking about on Slack or here in
I'll,
Zoom?
I'll go. There's content. So I can share my screen now and stop recording.